the text changes every half a second because we changed the value there to 25 million. Hey guys, today we will continue in our series where we go through the courses in FPGA Academy. Today we will continue with Lab 4, counters, and we will look at part 3. What will be special about part 3 is that we will be working with actually 50 MHz clock that will be provided by the board. So we will no more have to click on the keys to clock our designs, but we will be provided by clock that is in the board, and our design will show numbers 0 through 9 on 7-segment display, and this number will increment every second. So every second the number will increment by 1, so we will go 1, 2, 3 all the way to 9, then 0 and again. Before we go any further, if you haven't seen the previous parts, you can watch them on my YouTube channel. And let's look at this circuit. I'll try to explain how this circuit works. So we have two counters. The first counter has frequency 50 MHz, which is the frequency provided by the clock. But 50 MHz, that means 50 million cycles per second. But what we want is 1 cycle per second. We want to increment the counter only once a second, not 50 million times per second. So that means the first counter will be, but we have only clock that is 50 MHz. We don't have clock that is 1 hertz, one cycle per second. So we have to create this this counter. We will have our counter that will have actually the frequency 1 hertz, and what we will do is the first counter here will work as an enable for the second counter. So when this counter counts to 50 million, it will be the enable will be set to 1, and this counter will increment. So what that will do is we will this counter will also have clock 50 MHz, but will only increment when this will provide the enable. So this counter will be 26-bit counter. The other counter here, the 1 hertz counter, will be 4-bit counter. The faster counter here will count from 0 to 50 million, then it will set the enable to 1, and the slower counter will increment, and the slower counter will count from 0 to 9. And we will display 0 through 9 on our 7-segment display. So I hope you understand. If you don't understand it, you can write a comment and I will be more than happy to answer. And let's try to design this. So what we will do first, we will create an entity counter that we will be using in the next project. I have my part 3 here, and first let's create the counter. Not in Verilog, let's create VHDL. So I will copy this code. We will call it counter. And our counter will be actually very similar to part 2 in the previous what we have done in the previous video. So I will copy this to our architecture. We don't need the component here, and counter. So our counter will have clock as in, then it will have reset, or let's call it clear n, and then we will have enable. So it will have 3 inputs: clock, clear, and enable. And then we'll have output. And the output will be different based on how we configure the counter. So we will create generic that will be generic. And here we will define a number that will, so let's call it num. And then this will be integer. And the default value, let's say, will be 12. It doesn't really matter. And our output will be called q. It will be std logic vector, and it will be num minus 1 down to 0. So, for example, if the number here will be set to 12, our counter will be 12-bit counter, and this will be the output of the counter. So our variable here, let's call it count, and this will be our counter, so it will be also num minus 1 down to 0, and the initial value will be others 0. Then this process will change on clock, clear n, and enable. Clear n and enable will be actually synchronous, so we don't need them here. And on the rising edge of the clock, if enable is equal to, or if clear n is equal to 0, we will reset the counter. So we will do the same as here. Else, if enable is equal to 1, then we will increment the counter. Then we get our output here, and that's all we have to do. So this is gonna be our counter. Let's save it here as counter. And let's look at part 3. Our part 3 will have clock. Let's look at the pin assignments. And let's find clock. So here we can see clock 50. So that's gonna be our input. That's the clock provided by the board. So clock 50 will be our input. Then we will have switch as input that will enable the counter, and then hex that will show the number that will show the number. Here I have components that we have implemented in the previous videos, and this component shows our BCD or binary. In this case, we will only show 0 to 9, so the binary is equivalent to BCD, and it will show it on the 7-segment display. In this case, it will be hex 0. So we will import our component here in our part 3 here. So let's initiate counter enable. So that will be our enable counter here. Port map. And before port map, we have to do generic. I will just generics vhdl. So if we are doing mapping, we will just do generic map. So here we will do generic map, and then port map. Generic map, and our number. In this case, let's look at here. If we are importing this component, we will do this, similar to this. So, or this, or we actually don't have to do anything here or here. We can just say 26. That's because our first counter will be counting up to 50 million, and 50 million it has to be something that is the power of 2, and in this case the first number that is higher than 50 million is this number here, and that's 2 to the power of 26. So our counter will be 26-bit counter. So it will be 26, and port map. First clock, that will be the clock source, then clear. So our counter, let's create a wire, std logic, counter enable clear, signal std logic, like this. So let's shorten it. This signal will be for the clear. And what else do we need? Enable. There will be switch 0. So we will be controlling it by using the switch 0. And then our output. And our output will be signal. And it's gonna be counter enable Q, std logic vector 26 down to 0. So this is our counter. Let's set this as top level entity and try to run it. We don't have to run, we can just run the analysis. Let's see if we have any errors. And after, we need one more counter. Entity, yeah, I have to change this to component. And component. I'll just delete this. Let's try now. There should be semicolon here. And one more error, object unsigned is used but not declared. So here, and we have to import the library here as well. And now it should be fine. And here as well. Let's try it now. Okay, so we have our counter enable. Bin is used. Yeah, we have renamed this, so this will be count. So we have our counter enable. Next, we will create something like this. So we have our counter enable here. Then we have our another counter that is the slower counter here. And we will create a comparator here. that will compare the output and then set the enable. It will also set the reset for the counter. So it will set both enable and also the reset for the counter. So it will reset it. So we only count to 50 million, even though the counter can count up to this number. We will only count to 50 million and then we reset it. $20, $25 down to like this. So let's create another counter. This counter, so the next count, the second counter will only count to 9, which means it will be 4-bit counter. So 4, and let's create another wire like this, and yeah, another wire that will be called just counter Q, and this will be 3 down to 0. So this will have as the clock 50 as well, as clear, it will have as clear, it will have another, so this will clear when this is 9, so we also have to create another clear. Let's create another signal. Counter clear. Then enable will be this. It will be another wire signal. Counter enable. STD logic. And then our output will be this. So now here I will create a process that will change on the clock. Begin. And here, if this will actually change on if this changes. So if this is equal to, and now we will convert our this number, we will convert, or yeah, this will be unsigned. So we will convert it to integer. So we have our output here. We change it to integer, and we will compare it with number that is 50 million. So like this. Then counter enable is equal to 1, else then, and if counter enable is equal to 0. So if this number that we will get from the, so if this number is equal to 50 million, then we set this enable to 1. If this is equal to this, if this is equal to 50 million, we set this to 1, else it will be 0. I think it's like this. Let's try to, if the syntax is correct. And this is gonna be just counter 0. And we also need to reset this counter. So we will also set this to be 0, else it will be 1, because it's reversed. So if it's 50 million, it will also reset the counter to 0. And we will do the same for this counter, but this time it will change on this. And if this number is equal to 9, then we want to set this to 0. Okay. So if this number is equal to 9, then we reset to 0, which will reset the counter, else we set it to 1. So that's all for our counters, I think. And now we can connect it to our 7-segment display. So I'll initiate this. So let's call it seg0. It will be of this and this component, and port map. And it takes the binary number, that's this, as input and hex 0 as output. Okay, let's try to compile this. So what we have done is we created first counter, we set the enable for the second counter, we created second counter, and then the output of the second counter of this counter will be sent to this hex 7-segment display. Compilation is done, and one change I have done is I have changed this from 9 to 10, and that's because if it's set to 9, it will reset immediately when it's 9. So we will only see 8, and then it will go to 0. So I set it to 10, which will reset it. So we will still see 9, and then it will be reset on the 10. So now it's done, and let's try to program our board. And you can see it's counting all the way to 9 and resets to 0. And hopefully this should be done every 1 second. So you can see we have created a counter that counts every 1 second. Okay, let's continue. So now we will look at part 5. So let's see. So we will skip part 4 actually, because part 4 is, so what we will do is we will rotate the word DE, and for our board that's DE1 SOC. So we will rotate this word on the 7-segment displays. We have already done this in the previous video. It was done in part 3, 7-segment display. So if you haven't seen it, you can watch it and then come back here, because today we will reuse the code. So what will be different about this code is that instead of, so in the previous video, we have used switch to set the value of the counter. But this time we will have counter that will be counting from 0 all the way to some number. And this will change the text on the 7-segment display. And part 4 actually uses 4 7-segment displays. And in part 5, we use all the 7 segments, so 6 7-segment displays. So I'll just skip 4 and we will go straight to 6 7-segment displays. Let's look at here. I have here part 4, part 5. So we will be still using our counter here. So this is the same as in the previous one. We have 2 counters. One works as the enable for the second. and then the output will be sent as a select for MUX. So this will be counting from 0 all the way to 6. So it will be counting from 0 all the way to 6. This will be sent as a select to MUX, and it will select one of these actually 6, so there will be more. I can just copy this, and there will be more of these, you know, so there will be in total 6 of these. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So like this, 0, 1, 2, 3, 4, 5, and 6 will be clear. So that's what we will try to do. We will have a select here, and it will select one of these 6 inputs, and then it will display them on the 7-segment display. Let's do that now. I have my part 5 here. I will copy the code from part 3 here. I'll copy everything to part 5. Yes, and I will set part 5 as top level entity. So we will also want to count to 50 million because we will change the rotation every 1 second. We can try to set maybe 25 million, you know, and then it will be half a second and so on. So we can change this number to work for whatever we want, but we will set it to 1 second for now. And then here we will count all the way to 6. So 0 through 0 to 5, and then 6 will be reset. And our counter Q this time will not be the output, but we will use the code from part 5. I have it here. This is what all this code is what we have done in part 3 in this series. So again, it's this video here, 7-segment display, and we have created this instance or this entity. It was part 6, so this time I will rename it, and I will call it rotate DE1, and it will take hex 0. It will take these hexes as inputs, so I'll just change that to 5, 4, 3, 2, hex 2, and it will have this is gonna be our select. Our select is gonna be 2. It's gonna be 3 bits. That's our select here, and that's I think that's 3 bits. So 2 down to 0. That's gonna be our select, and here I will change this to select. These are all the muxes for each of the 7-segment display. So each of the MUX will have this select, and these are the options, the inputs. So let's look at the first one, for example. This one, if the select is 0, it will choose this one. If it's 1, it will choose this one, and so on. And then it rotates, so this is different than the first one, and so on. So, and here I will change it to be lowercase. So 1, 3, 2, 4, and 5. And that's all I have to change, I think, in this code. And also this name. So this is done, and we will import this as entity to our part 5 here. Component. Let's change this, and component. And let's initiate this here. So let's call it display text txt, and port map. So our select will be the output of the counter. Then we have all of our hex, all of our hex. So hex 0, hex 1, hex, and I'll copy this. So 5, 4, 3, 2, and we don't need this. So again, we have our switch. This switch will enable the counting. So if I switch this to 1, oh, it's switched to 1 now. So if I switch it to 0, it will not be counting, and then it will display the text using this component. It will display the text, and the counter will be used as select. Let's try to run this. And we have component counter, and here I don't have architecture here. So architecture. Okay, let's see now. Clock 50 is used but not declared. Oh, and of course we have to change this to clock 50. And counter Q is 4-bit, but we want just 3-bit. We don't want 4-bit. Yes. And 3-bit will give us 8 as the maximum number, and that will be compared with 6. Okay. And here, okay, 3. So we have to also change this to be 2 down to 0. It would be maybe better to use some number that we can change, and then all these values change. But this is a simple design, so we don't have to do it now, but it's better practice to use it. And compilation is done. We can look at compilation report, and we can see that we have used 31 registers. If you look at part 5, we have 3-bit and 26-bit, so that's 29, and yeah, that's almost 31. Maybe we use some, I don't know. Well, anyway, so let's try to compile. Let's try to run it on our board. And so now you can see that we have some text displayed on the board, and when I enable this switch, it should start to rotate. You can see every second this text rotates. But I don't actually like that it shows 1 ED. So let's try to fix that. Let's try to show DE1. And And also let's speed it up a little bit. So let's change this to 25. That will be half a second for the change. And here in the rotate DE, it's starting DE1. I think the problem is in the order, so this should be 5, 4, 3, 2, 1, and 0. And compile. So compilation is done. Let's program. So you can see it's not moving now. And when I change the switch, you can see it's moving. So this is how it should be moving. If we look at the, so it starts like this and then it goes backwards. So this is how it was supposed to be shown. So let's look at it once more. So you can see the text changes every second. So actually this text changes every half a second because we changed the value there to 25 million. So this changes every half a second. It's pretty cool. So that's gonna be all for today. We have finished part 5, and that was the last part. So next time we will look at timers and real-time clocks. Let's look at it real quick. So the purpose of this exercise is to study the use of clocks in time circuits. Okay. And yeah, there's some Morse code here. So this seems a little bit more, little bigger circuit. So we will do this next time. So if you want to see this, don't forget to subscribe, and I'll see you in the next one. Bye.